Hey, welcome in, everybody. Welcome to the stream. I am Sam Spade, and welcome to Sam Spade Tech. Hey, sorry about yesterday. If you guys were here on yesterday's stream, I have no idea what exactly happened. I was streaming and all sorts of things. Like every time I stream, like something goes awry. Like I don't know if it's just me, if I have like bad luck with streaming, but like every single time I stream, one app or another just does not function as advertised. And yesterday, it just so happened to be OBS. So OBS like came up with a prompt. It said like cannot record, yada yada yada, which was weird because I wasn't recording at the time. So I'm not sure what caused that, but everything froze. I could not even pull up Task Manager. So not great, but hey, computers are finicky creatures. Um, I bought this computer about a year ago. It was a pre-built. I don't think anything was damaged in transit because that is one of the issues that these companies do have. Is the mail handlers, either UPS, USPS, FedEx, any of them. They're not very gentle, especially when it comes to big, heavy boxes. They just kind of throw them in there. But yeah, yesterday I was live for like 2 hours. I wasn't recording, and then hard crash. So, but it does give me an opportunity to showcase another handy little app that I found. I think, yeah, because the last time when I was having issues, I did contact technical support over at SkyTech, right? Because that's where I bought it, SkyTech. And uh, they said, grab this app. Where is it? Let me see. Give me 1 second. It's not this. It's called Who Crashed, I believe, is the name of it. Yeah, Who Crashed. So this little app, um, because I was having like RAM issues on this PC. So, and honestly, that's like 90% of what you do with computers
Draw the
is
cat eyes sharp enough to kill a
whoa.
man. You did some bad things, but I'm the worst of them.
No way. Falling asleep. Oh, what? He's falling asleep? No way. Well, I did get a late start. Uh, Cooper was falling asleep on the swings. No way. Oh. He said goodbye to the park. He's like, bye park. Bye. Bye tree. He's so cute. He'll say like bye tree, bye car, bye plants, bye dog, bye mama. He's so cute. Well, come on home. Come on home. Um, yeah, and I honestly don't even know what I am gonna stream today. I figured if anyone else has a tech dilemma, they could call in to the Discord channel. Only problem is I got to build the Discord channel first. So we can go about that, build a new Discord channel for the tech channel, and then maybe do a call-in show. What do you guys think of that? I don't know. I got 2 viewers over on YouTube, but it could be Botrix. I don't know. It probably is Botrix for all I know. But um, yeah. So and I forget what the issue was before, but a lot of it seems to be either related to or in conjunction with the graphics drivers. So like my graphics card drivers. So either it's not that it's eating up too much resources. It's like the shader cache. I think the shader cache like is corrupting the drivers somehow, or the drivers go out of date. I don't know. From what I was reading online, it said that your your graphics drivers can just become corrupt. So you install them, they're just fine. They're working great for a little while, and then they just become corrupt somehow. I am not 100% sure how that happens, what causes that, but here we are, you know. So yeah. So it's all good. But anyway, guys, this handy little app, I was directed to it by SkyTech, and it's got dump files, local drivers, tools, different things you can run here. But all you got to do is hit analyze. And this was even like an hour after the crash because I reinstalled it, and then because I had taken it off there for a while. Um, but it grabs the logs. So right here on Friday, it says video engine timeout detected, right? And then it tells you basically this is a video related crash. A DirectX driver was identified on the stack. Since there is no other responsible driver detected, it is suggested you look for an updated driver for your graphics hardware. It's also possible that your graphics hardware was non-functional or overheated. That's possible. It's possible that it overheated. I wouldn't think so, because I mean, all I was doing was streaming, so I wasn't streaming and what do you call it? I wasn't streaming and playing a game at the same time. So compute 0, copy 1, timer 0, security 1. Video JPEG. So it's the video codec engine keeps pinging it at 100%, and I don't know why. It's very strange. May have to look that up. It was on copy 1, so we got copy, copy. And then we got video codec engine. I don't know what this was on before. Compute 0, something. So I may have to look that up as to why my video codec engine is jumping up and down so much. Take a look here. Yeah, I'm not sure. That didn't help. Dun, 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 dun. See, this one just says that it's pegged at 100%. And I wasn't, at the time, I wasn't playing any video games. I was just streaming to less channels than I normally stream to. Normally I'm on uh, YouTube, Kick, TikTok, and possibly, whoa, what the was that? Uh-huh. Oh yeah, that was fun. Yeah, my signal RGB also, I had to fix that, but that shouldn't have anything to do with the video codec engine. I don't even know what to say. It's like it's not pegged at 100%. Let's just see what this one says. So 100% usage of video codec. So mine's not 100%, but let's see what this says. This is just playing video on YouTube. Okay, here's something. So if that doesn't do it, you can use Film Merit or a comparable program to repair, disable malfunctioning codec. So perhaps, hmm, yeah, disable hardware acceleration. I've disabled hardware acceleration in a lot of the programs. Looks like there's a couple apps in here, but again, I don't know if this is not supposed to look like this. I am streaming, so there's obviously going to be some encoding, but it shouldn't be going to 100% and back down, right? So driver version, driver dates 11/06/25. So that's a newer driver. DirectX 12, PCI bus 3, 16, hardware reserve. I just don't like that it's jumping from, see, like, look at this. This is my integrated graphics, and it's fairly steady. But then you got the video codec, and it's like ding, 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 ding. It just doesn't make sense why it's doing that. But anyway, we updated the graphics kernel. We're gonna monitor this. The only other thing I can do, and I'm not gonna do it right now, but go back over to my other OS, because I've got a couple other OSs installed on here, and see if the driver over there does it. But for right now, we're okay. We're running at 15 gigs of memory. And video codec is still bouncing. So I don't know. We'll see. We'll see what happens here. But what we were going to do is build ourselves a Discord. You know what? I didn't think of that. I wonder if it's my wallpaper. Let me change the wallpaper, because I just installed the wallpaper engine, and now let me look at it. Now it's even higher. Oh, it doesn't save that? Why wouldn't it save that? Huh. Now it's even higher. It's going ping, 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 ping. It could be wallpaper engine. Don't know. Don't know, don't know. All right, anywho. It could be the wallpaper engine. I did just add the wallpaper engine. I could try quitting out of that and see if that fixes it real quick. Quit this too. Quit that. Quit wallpaper engine. Take a look. And what up? He's sleeping. What? So he was on the swings? Which park did you go to?
It was this one in Castleberry. It's a really old park, but it's fenced in. So I was like,
Yeah.
and no one was there because it's like an older kid running, all fenced in.
Yeah.
So go and go and go. And finally, I put him on. He just nodding off. He's only this like good, and that's not very trying to keep his eyes open. And he was starting to like slump over, and I was like, "You want to get out?" He's like, "Pull him out." On the ground, he's like, "Bye, tree." Like, okay.
Oh my god, that's so funny.
Yeah. So yeah, he's out.
Well, there you have it.
He can't communicate like exactly what he wants, but he communicates to where it's like, I know.
Yeah.
It's like just like bye
Yeah.
park.
Bye park.
Instead of saying
Right.
I'm tired or I'm
Right.
sleepy, he starts saying
Right.
bye to the park.
He figures it out. Like me, he just figures stuff out. Yeah, it looks like it says I got two viewers on YouTube, but it could be just bot tricks for all I know. No, it's okay. I'm just trying to still figure out why my computer crashed yesterday. Hmm.
Later.
Oh.
I don't know if I know what this is.
Oh, it's a card.
Do you think it's holiday photos of the dog?
No.
They never did anything like that?
And she spelled your name with a K.
I know. Which is funny because she spelled it right every other time.
I know.
Okay, one time my
And
grandma
Dad
spelled my
definitely
name
didn't
wrong,
do
and
it.
I'm named after her. Like when she got old, my name wrong, and I'm literally named after her, spelled the exact same name. Same first, like name, same last name.
Interesting.
Old.
Old people. All right, let's close this down. I am gonna jump on Discord here in a second. Here we go. You okay over there? We're gonna create a no. What to do? How do I? Heck, why did it? I hate Discord. I really do. It's useful for what it is and what it does, but does it really have to be this difficult? Like, it's almost too simplistic. You know what I mean? Right there. All right. We're creating a server. We created our own gaming, friends, study group, school club, local community. It's none really there. We'll create our own. Fan for a club or community. Sure. And we'll call this. Call it Sam Spade Tech. And I got should have some pictures here. Thumbs? There it is. We'll use this one. There it is. All right, we're here. Voice channels. Settings. The lobby. Permissions. It's not private. Permission. Okay. We got the lobby. That's for everybody. And then we've got duplicate this. Duplicate the channel. This would be name that real quick. Is it? Wait, save. Private channel. Save that one. That's a private channel. So everybody can hang in the lobby, and then I can drag them into line one, etc., etc. Invite to voice. Okay, so then I can invite people to there. Where did it go? There we go. My BADSPADE server, and then this is the newest one, just with a couple voice lines in it. So you guys want to call in with any tech dilemma? Feel free to call in. Hey, Cat's here. Welcome in, Cat. How you doing? duplicate this one. Oops, line 2. Channel. Just do line 3. So these are all private channels. All right, we got the lobby. So anyone can be in the lobby. We got general. Kind of sleepy. Yeah, I'm kind of sleepy too. We just take a nap. Take a nap and I could just delete my stream. I don't know. I am kind of tired. I am kind of tired.
Let's break it down in simple terms. The GPU engine refers to specific parts of your graphics processing unit that handle different tasks. A graphics processing
wanted to
unit
see
is
that?
made up
Oh,
of
sorry.
several independent engines, each designed for specialized operations like three-dimensional rendering, video decoding, and video encoding. These engines work together, allowing your graphics processing unit to handle various workloads efficiently. When you open Task Manager, you will see a column labeled GPU engine. This column shows which engine a running process is using. For instance, if you are playing a game, it might primarily use the three-dimensional engine. On the other hand, if you are watching a video, that application might use the video decode engine. If your computer has multiple graphics processing units, Task Manager will also indicate which graphics processing unit and engine a specific process is utilizing. This is particularly useful for users with more advanced setups. Task Manager usually displays a selection of the most active GPU engines, so you can see which ones are relevant to your current tasks. You can even choose to view different engines from the available list to monitor specific workloads. The overall GPU utilization shown in Task Manager is based on the activity of the busiest engine. This gives you a clearer picture of how your graphics processing unit is being used during tasks like gaming or video playback. From an application perspective, Task Manager helps you monitor how different applications interact with the graphics processing unit. It shows which parts of the graphics processing unit hardware are engaged. This can be helpful for troubleshooting performance issues or optimizing resource use. In short, the GPU engine in Task Manager allows you to identify and monitor the distinct processing units within the graphics processing unit that are active for particular applications.
Alrighty. That still isn't. Doesn't look like that. The only thing that I'm using right now is OBS, really. I cut that. Hit apply. Let's see what that does. Nothing. turned off the wallpaper engine and that didn't help. Didn't seem to make a difference. Yeah, I don't know what's causing it. I'm not recording. And I don't have the replay buffer on. Let's see what happens when I start the replay buffer. 3, 2, 1. Doesn't look like it changed much. The RAM didn't even change. CPU is barely even being utilized, so that's good. That was a big dip. Why was that? What was that dip? Is that into memory? What the heck? That's weird. If I go to memory, monitor the memory for a few seconds. And then come back here, it'll dip. What? That doesn't make any sense. Anyway. Hmm. Mm, 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 mm. Mm, 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 mm. Oh, that's nice. I do like that better. Refresh this one. Is it hot in here? Feels hot. Feels hot in here. Hmm. Mm, mm, mm. Hmm. I love watching these videos. Windows is dying. Let's see what this guy has to say. Hold on now. Okay, that's muted. Headphones in.
Is already so Windows 11 is already kind of dying because there is a huge fraction of people who are not switching from Windows 10 to Windows 11. Even after security updates in the US ended, people still aren't switching. Now, the EU successfully got Windows to extend the security updates for Windows 10, but technically I think that's only supposed to be if you're in the EU. There is an easy way to cheese the system, though, to get Windows 10 updates still, but people aren't switching. Even though Microsoft has been pushing people really hard to switch to Windows 11, people still aren't switching. And I'm sure a big reason for that is that people have perfectly fine computers that won't work with Windows 11. I'm sure that's a factor. Like, there is a specific chip you need on your motherboard for Windows 11 to properly install. There's a way around it, but why would you do that? But people not making the switch to Windows 11 is not mostly to do with this hardware check. It really isn't. 29% of Steam users are still on Windows 10, which is a pretty big chunk. Intel, the computer company, also claims that 500 million people could switch to Windows 11, but don't do it. Now, personally, I am on Windows 11 because when I built my new computer a couple years ago, Windows 11 was just there, so I installed it. Little did I know, it was significantly worse than Windows 10 in so many ways, and it was already too late to, like, really roll it back. Like, for example, I didn't know the File Explorer was gonna basically just not work. Like, the File Explorer on Windows 11 is hot garbage. It doesn't search anything at all at any kind of speed whatsoever. It makes zero sense, because the craziest part is with
he's talking fast even though it's not sped up. So yeah, I'll slow it down.
this stupid File Explorer is if you install a third-party software, it finds everything in your computer within like nanoseconds. It's actually insane that third-party software can just do the thing that Microsoft was supposed to do with their operating system. Like, what kind of trillion-dollar company can't make a File Explorer for their goddamn operating system, but some nerd in his basement can make a third-party app that works instantaneously and way better than Windows? Like, what is this? The fact that Microsoft has any money whatsoever is a crime against humanity because they can't make anything work to save their life.
This guy's funny. Who's this guy? Oh, his name is Spattins?
Lives. And then Microsoft is also trying to shove
Sounds
AI
like a spans.
into every aspect of Windows 11, make it even.
This is what makes me sick. Is fucking AI is cool, but I don't need it shoved down my throat. It's already everywhere. I don't need it invading my already installed operating system, and now all of a sudden it's on my computer doing God knows what.
Slower now. Like, I'm sorry, Copilot could be cool, okay? It could be a cool thing, but all I'm seeing is this stuff being shoved into Windows 11, and somehow Windows 11 keeps getting worse. It's almost like lots of forms of AI suck and are bad and should be implemented literally everywhere. Like, it would not surprise me if Microsoft came out and said, hey guys, sorry, we vibe coded File Explorer. That's why it blows ass. And the most amazing part about File Explorer is the way that Microsoft decided to make File Explorer faster was to preload it on startup, because that makes sense. Oh yeah, this slow clunky thing, instead of making it faster, let's just preload it on startup so the computer starts even slower. Like, I genuinely don't know how
Yeah, they're fucking up so bad. That's why I want to find a Linux distro that is pretty easy to use and do like a test run of it and only use that for like 30 days. One, to see if I could do it and still have like all the applications that I need, starting with streaming. So I'd have to set up my stream over on Linux. I just haven't done it yet. And with the holidays, like, you know, I want to have some time to actually do it. We're going to be out of town, so but until then, I've been kind of poking around at different Linux distros, so I've got a few options that I'd like to try. So there's CachyOS, Manjaro, or what's the other one? Zorin, which is probably like the simplest of the three. It's more of like a mom and pop type OS, which would be good because then it would show people like how easy Linux could be for them. So I don't know. Those are the three options.
Microsoft managed to fumble their own file explorer this bad to where they decided to have to preload it on the system to get it to work. And the worst part is, it's really not even that much faster, and now it uses like double the RAM. So thanks, Microsoft. I really appreciate your contribution to society here. Oh, and the best part about that file explorer update where it preloads everything, if you have dark mode enabled, it will sometimes just flashbang you when you first open file explorer, because that makes sense. So Microsoft had to preload all of your index files to get it to even work properly, and now it flashbangs you. And get this, it was a known issue. Microsoft pushed this update with this known issue. If you ever have a bug in Windows 11, rest assured knowing it will never ever get fixed, because they can't do it. They can't fix anything to save their lives. And I think the funniest part about people not switching to Windows 11 from Windows 10 is that if enough people don't switch, Microsoft has no choice but to keep giving them security updates, because if like 30% of the people using your operating system refuse to switch over, that is your problem now. If people aren't updating to Windows 11 and a huge install base is still on Windows 10, you still have to update security for them, because if you don't and something happens, Windows is screwed. Like, Microsoft is screwed. Like, imagine all the headlines if 30% of Windows users have this massive vulnerability that can be exploited. Like, imagine how bad that would look for Microsoft. They literally have to keep giving security updates if enough people stay on Windows 10. But yeah, Microsoft are clowns, and I hope they go bankrupt. Thank you for watching. I hope you enjoyed. Click the answer to check more of my content, and have a good one.
How much of wrestling is fake?
How much is, well, that's a good question. I want to know this one myself.
0.
None at all?
Nothing.
Now, you mean to tell me that these that's on a television, the tube, now, as I said, I'm not talking about live, I'm talking about on the tube, that none of that is fake whatsoever?
Let me requalify my answer to the public and to you. I can't vouch for every match. Anytime two individuals go into the ring, you don't know what's going on. You got two guys bowling for the finals. And if one guy, somehow, I don't know how,
The Macho Man.
How many calculations do you think your graphics card performs every second while running video games with incredibly realistic graphics? Maybe 100 million? Well, 100 million calculations a second is what's required to run Mario 64 from 1996. We need more power. Maybe 100 billion calculations a second? Well, then you would have a computer that could run Minecraft back in 2011. In order to run the most realistic video games such as Cyberpunk 2077, you need a graphics card that can perform around 36 trillion calculations a second. This is an unimaginably large number. So let's take a second to try to
Per second? What?
conceptualize it. Imagine doing a long multiplication problem once every second. Now let's say everyone on the planet does a similar type of calculation, but with different numbers. To reach the equivalent computational power of this graphics card and its 36 trillion calculations a second, we would need about 4,400 Earths filled with people, all working together and completing one calculation each every second. It's rather mind-boggling to think that a device can manage all these calculations, so in this video we'll see how graphics cards work in two parts. First, we'll open up this graphics card and explore the different components inside, as well as the physical design and architecture of the GPU, or Graphics Processing Unit. Second, we'll explore the computational architecture and see how GPUs process mountains of data and why they're ideal for running video game graphics, Bitcoin
That's unfathomable.
mining, neural networks, and AI. So stick around and let's jump right in. This video is sponsored by Micron, which manufactures the graphics memory inside this graphics card. Before we dive into all the parts of the GPU, let's first understand the differences between GPUs and CPUs. Inside this graphics card, the Graphics Processing Unit, or GPU, has over 10,000 cores. However, when we look at the CPU, or Central Processing Unit, that's mounted to the motherboard, we find an integrated circuit or chip with only 24 cores.
I was going to say, how much? Did it say 10,000?
So, which one is more powerful? 10,000 is a lot
Holy shit.
more than 24, so you would think the GPU is more powerful. However, it's more complicated than that. A useful analogy is to think of a GPU as a massive cargo ship and a CPU as a jumbo jet airplane. The amount of cargo capacity is the amount of calculations and data that can be processed, and the speed of the ship or airplane is the rate at which how quickly those calculations and data are being processed. Essentially, it's a trade-off between a massive number of calculations that are executed at a slower rate versus a few calculations that can be performed at a much faster rate. Another key difference is that airplanes are a lot more flexible since they can carry passengers, packages, or containers and can take off and land at any one of tens of thousands of airports. Likewise, CPUs are flexible in that they can run a variety of programs and instructions. However, giant cargo ships carry only containers with bulk contents inside and are limited to traveling between ports. Similarly, GPUs are a lot less flexible than CPUs and can only run simple instructions like basic arithmetic. Additionally, GPUs can't run operating systems or interface with input devices or networks. This analogy isn't perfect, but it helps to answer the question of which is faster, a CPU or a GPU. Essentially, if you want to perform a set of calculations across mountains of data, then a GPU will be faster at completing the task. However, if you have a lot less data that needs to be evaluated quickly, then a CPU will be faster. Furthermore, if you need to run an operating system or support network connections in a wide range of different applications and hardware, then you'll want a CPU. We're planning a separate video on CPU architecture, so make sure to subscribe so you don't miss it.
Okay.
But let's now dive into this graphics card and see how it works. In the center of this graphics card is the printed circuit board, or PCB, with all the various components mounted on it. And we'll start by exploring the brains, which is the Graphics Processing Unit, or GPU. When we open it up, we find a large chip or die named GA102, built from 28.3 billion transistors. The majority of the area of the chip is taken up by the processing cores, which have a hierarchical organization. Specifically, the chip is divided into 7 graphics processing clusters, or GPCs, and within each processing cluster are 12 streaming multiprocessors, or SMs. Next, inside each of these streaming multiprocessors are 4 warps and 1 ray tracing core, and then inside each warp are 32 CUDA, or shading cores, and 1 tensor core. Across the entire GPU are 10,752 CUDA cores, 336 tensor cores, and 84 ray tracing cores. These 3 types of cores execute all the calculations of the GPU, and each has a different function. CUDA cores can be thought of as simple binary calculators with an addition button, a multiply button, and a few others, and are used the most when running video games. Tensor cores are matrix multiplication and addition calculators and are used for geometric transformations and working with neural networks and AI. and ray tracing cores are the largest but the fewest, and are used to execute ray tracing algorithms. Now that we understand the computational resources inside this chip, one rather interesting fact is that the 3080, 3090, 3080 Ti, and 3090 Ti graphics cards all use the same GA102 chip design for their GPU. This might be counterintuitive because they have different prices and were released in different years, but it's true. So why is this? Well, during the manufacturing process, sometimes patterning errors, dust particles, or other manufacturing issues cause damage and create defective areas of the circuit. Instead of throwing out the entire chip because of a small defect, engineers find the defective region and permanently isolate and deactivate the nearby circuitry. By having a GPU with a highly repetitive design, a small defect in one core only damages that particular streaming multiprocessor circuit and doesn't affect the other areas of the chip. As a result, these chips are tested and categorized or binned according to the number of defects. The 3090 Ti graphics card have flawless GA102 chips, with all 10,752 CUDA cores working properly. The 3090 has 10,496 cores working. The 3080 Ti has 10,240, and the 3080 has 8,704 CUDA cores working, which is equivalent to having 16 damaged and deactivated streaming multiprocessors. Additionally, different graphics cards differ by their maximum clock speed and the quantity and generation of graphics memory that supports the GPU, which we'll explore in a little bit. Because we've been focusing on the physical architecture of this GA102 GPU chip, let's zoom into one of these CUDA cores and see what it looks like. Inside this simple calculator is a layout of approximately 410,000 transistors. This section of 50,000 transistors performs the operation of A times B.
I still don't think it's normal science. This is dark magic.
Plus C, which is called fused multiply and add, or FMA, and is the most common operation performed by graphics cards. Half of the CUDA cores execute FMA using 32-bit floating point numbers, which is essentially scientific notation, and the other half of the cores use either 32-bit integers or 32-bit floating point numbers. Other sections of this core accommodate negative numbers and perform other simple functions like bit shifting and bit masking, as well as collecting and queuing the incoming instructions and operands, and then accumulating and outputting the results. As a result, this single core is just a simple calculator with a limited number of functions. This calculator completes one multiply and one add operation each clock cycle, and therefore with this 3090 graphics card and its 10,496 cores and 1.7 gigahertz clock, we get 35.6 trillion calculations a second. However, if you're wondering how the GPU handles more complicated operations like division, square root, and trigonometric functions, well, these calculator operations are performed by the special function units, which are far fewer, as only 4 of them can be found in each streaming multiprocessor. Now that we have an understanding of what's inside a single core, let's zoom out and take a look at the other sections of the GA102 chip. Around the edge, we find 12 graphics memory controllers, the NVLink controllers, and the PCIe interface. On the bottom is a 6 megabyte Level 2 SRAM memory cache. And here's the GigaThread engine, which manages all the graphics processing clusters and streaming multiprocessors inside. Now that we've explored this GA102 GPU's physical architecture, let's zoom out and take a look at the other parts inside the graphics card. On this side are the various ports for the displays to be plugged into. On the other side is the incoming 12-volt power connector. And then here are the PCIe pins that plug into the motherboard. On the PCB, the majority of the smaller components constitute the voltage regulator module, which takes the incoming 12 volts and converts it to 1.1 volts and supplies hundreds of...
That's crazy. That's absolutely crazy. So all of those calculations only run on 1.1 volts of electricity. Just to put it in perspective, coming out of the wall socket is 120 volts. And that's overkill. Because like majority of our appliances and things that we plug in don't use that much power. They don't. So you're telling me that the chip itself only needs 1.1 volts, but yet the power supply is, well, it's in watts, but
of watts of power to the GPU. Because all this and so incoming 12 volts and converts it to 1.1 volts and supplies hundreds of watts of power to the GPU. Because all this power heats up the GPU, most of the weight of the graphics card is in the form of a heat sink, with 4 heat pipes that carry heat from the GPU and memory chips to the radiator fins, where fans then help to remove the heat. Perhaps some of the most important components, aside from the GPU, are the 24 gigabytes of graphics memory chips, which are technically called GDDR6X SDRAM, and were manufactured by Micron, which is the sponsor of this video. Whenever you start up a video game or wait for a loading screen, the time it takes to load is mostly spent moving all the 3D models of a particular scene or environment from the solid-state drive into these graphics memory chips. As mentioned earlier, the GPU has a small amount of data storage in its 6 megabyte shared level 2 cache, which can hold the equivalent of about this much of the video game's environment. Therefore, in order to render a video game, different chunks of scene are continuously being transferred between the graphics memory and the GPU. Because the cores are constantly performing tens of trillions of calculations a second, GPUs are data-hungry machines and need to be continuously fed terabytes upon terabytes of data. And thus, these graphics memory chips are designed kind of like multiple cranes, loading a cargo ship at the same time. Specifically, these 24 chips transfer a combined 384 bits at a time, which is called the bus width, and the total data that can be transferred, or the bandwidth, is about 1.15 terabytes a second. Wow. In contrast, the sticks of DRAM that support the CPU only have a 64-bit bus width and a maximum bandwidth closer to 64 gigabytes a second. One rather interesting thing is that you may think that computers only work using binary ones and zeros. However, in order to increase data transfer rates, GDDR6X and the latest graphics memory, GDDR7, send and receive data across the bus wires using multiple voltage levels beyond just 0 and 1. For example, GDDR7 uses 3 different encoding schemes to combine binary bits into ternary digits, or PAM3 symbols with voltages of 0, 1, and -1. Here's the encoding scheme on how 3 binary bits are encoded into 2 ternary digits, and this scheme is combined with an 11-bit to 7 ternary digit encoding scheme, resulting in sending 276 binary bits using only 176 ternary digits. The previous generation GDDR6X, which is the memory in this 3090 graphics card, used a different encoding scheme called PAM4 to send 2 bits of data using 4 different voltage levels. However, engineers in the graphics memory industry agreed to switch to PAM3 for future generations of graphics chips in order to reduce encoder complexity, improve the signal-to-noise ratio, and improve power efficiency. Micron delivers consistent innovation to put...
What the fuck did he just say? I mean, I kind of understand it. So that basically they went with a new language of voltage encoding so that it can process more data by encoding it into a secret language. Yeah, it seems like more and more we're going to need AI to do things like this, like encoding and decoding weird language stuff. I'm sure AI could design a better computer chip slash microchip, and it would just, that's probably where quantum computers came from, honestly. Let's be serious. Like, because I don't know how quantum computers work. I'm sure that this branch education has a video on it, but that definitely seems like black magic. So
push the boundaries on how much data can be transferred every second, and to design cutting-edge memory chips. Another advancement by Micron is the development of HBM, or the high bandwidth memory that surrounds AI chips.
Right.
HBM is built from stacks of DRAM memory chips and uses TSVs, or through silicon vias, to connect the stack into a single chip, essentially forming a cube of AI memory. For the latest generation of high bandwidth memory, which is HBM3E, a single cube can have up to 24 to 36 gigabytes of memory, thus yielding 192 gigabytes of high-speed memory around the AI chip.
What? 192 just around the CPU chip? Wow.
Next time you buy an AI accelerator system, make sure it uses
AI accelerator system? I didn't know you could buy one of those.
Micron's HBM3E, which uses 30% less power than the competitive products.
What the there's competitive products?
However, unless you're building an AI data center, you're likely not in the market to buy one of these systems,
No,
which
I'm
cost
not.
between $25,000 to $40,000
Definitely not.
and are on back order for a few
They're
years.
fucking back ordered, by the way. So you can't even get them. Even if you wanted to, can't get them. $40,000, no problem. They're on back order.
If you're curious about high bandwidth memory or Micron's next generation of graphics memory, take a look at one of these links in the description.
What the fuck? That's gonna be wild, dude. Could you imagine that in a graphics card? 192 gigs just on the chip? Like on the chip itself.
Alternatively, if designing the next generation of memory chips interests you, Micron is always looking for talented scientists and engineers to help innovate on cutting-edge chips. And you can find out more about working for Micron using this link.
Do it.
This may be the last ad you ever see.
Oh, shit.
Because-
Am I about to die? Jesus.
With the free ad block
Oh,
extension from
ad block.
Capital One Shopping, you can say goodbye to ads on sites.
This is the last ad you're
Now that
ever
we've
gonna
explored
see.
many
Jesus. That sounds like a threat.
of the physical components inside this graphics card and GPU, let's next explore the computational architecture and see how applications like video game graphics and
There
Bitcoin
he is.
mining
Look at that guy. What video game is that?
run what's called embarrassingly parallel operations.
What the fuck? Is that the scientific term? Embarrassingly parallel operations? That does not seem like a technical term.
Although it may sound like a silly name,
It is.
embarrassingly parallel is actually a technical classification of computer problems
Stop it.
where little or no effort is needed to divide the problem into parallel tasks. And video game rendering and Bitcoin mining easily fall into this category. Essentially, GPUs solve embarrassingly parallel problems using a principle called SIMD, which stands for Single Instruction Multiple Data, where the same instructions or steps are repeated across thousands to millions of different numbers. Let's see an example of how SIMD, or Single Instruction Multiple Data, is used to create this 3D video game environment.
All right.
As you may know already, this cowboy hat on the table is composed of approximately 28,000 triangles,
I knew that.
built
I could tell just by
by connecting together around 14,000 vertices,
Come on.
each with X, Y, and Z coordinates. These vertex coordinates are built using a coordinate system called model space, with the origin of 0, 0, 0 being at the center of the hat. To build a 3D world, we place hundreds of objects, each with their own model space, into the world environment, and in order for the camera to be able to tell where each object is relative to other objects, we have to convert or transform all the vertices from each separate model space into the shared world coordinate system, or world space. So, as an example, how do we convert the 14,000 vertices of the cowboy hat from model space into world space? Well, we use a single instruction which adds the position of the origin of the hat in world space to the corresponding x, y, and z coordinate of a single vertex in model space. Next, we copy this instruction to multiple data, which is all the remaining x, y, and z coordinates of the other thousands of vertices that are used to build the hat. Next, we do the same for the table and the rest of the hundreds of other objects in the scene, each time using the same instructions but with the different object's coordinates in world space, and each object's thousands of vertices in model space. As a result, all the vertices and triangles of all the objects are converted to a common world space coordinate system, and the camera can now determine which objects are in front and which are behind. This example illustrates the power of SIMD, or Single Instruction Multiple Data, and how a single instruction is applied to 5,629 different objects with a total of 8.3 million vertices within the scene, resulting in 25 million addition calculations.
What?
The key to SIMD and embarrassingly parallel programs is that every one of these millions of calculations has no dependency on any other calculation, and thus all these calculations can be distributed to the thousands of cores of the GPU and completed in parallel with one another. It's important to note that vertex transformation from model space to world space is just one of the first steps of a rather complicated video game graphics rendering pipeline, and we have a separate video that delves deeper into
I wanted to watch that one.
each of these other steps. Also, we skipped over the transformations for the rotation and scale of each object, but factoring in these values is a similar process that requires additional SIMD calculations.
Of course.
Now that we have a simple understanding of SIMD, let's discuss how this computational architecture matches up with the physical architecture. Essentially, each instruction is completed by a thread, and this thread is matched to a single CUDA core. Threads are bundled into groups of 32 called warps, and the same sequence of instructions is issued to all the threads in a warp. Next, warps are grouped into thread blocks, which are handled by the streaming multiprocessor. And then finally, thread blocks are grouped into grids, which are computed across the overall GPU. All these computations are managed or scheduled by the GigaThread engine, which efficiently maps thread blocks to the available streaming multiprocessors. One important distinction is that within SIMD architecture, all 32 threads in a warp follow the same instructions and are in lockstep with each other, kind of like a phalanx of soldiers moving together. This lockstep execution applied to GPUs up until around 2016. However, newer GPUs follow a SIMT architecture, or single instruction multiple threads. The difference between SIMD and SIMT is that while both send the same set of instructions to each thread, with SIMT, the individual threads don't need to be in lockstep with each other and can progress at different rates. In technical jargon, each thread is given its own program counter. Additionally, with SIMT, all the threads within a streaming multiprocessor use a shared 128 kilobyte L1 cache, and thus data that's output by one thread can be subsequently used by a separate thread. This improvement from SIMD to SIMT allows for more flexibility when encountering warp divergence via data-dependent conditional branching and easier reconvergence for the threads to reach the barrier synchronization.
Sure, you lost me.
Essentially,
I was with you on the world coordinates and vertexes and 3D. I was with you there, and then
Newer architectures of
went off
GPUs
the
are more
rails, but-
flexible and efficient, especially when encountering branches in code. One additional note is that although you may think that the term
Like, how did we get here? How did they figure this shit out?
warp is derived from warp drives, it actually comes from weaving, and specifically the Jacquard loom.
Oh,
This loom from 1804 used programmable punch cards to select specific threads out of a set to weave together intricate patterns.
oh.
As fascinating as looms are, let's move on.
What? I was fascinated for a
Oh,
second.
Capital One, my team's transformer-based AI model, built
the-
using contextual data.
No, thank you.
The final topics we'll explore are Bitcoin mining,
Yes.
tensor cores, and neural networks.
Okay.
But first, we'd like to ask you to like this video.
Like this video,
Write a quick
guys.
comment below.
These guys are good. I like these videos that they're doing. I want to check out that next one, the 3D, how video game graphics are made, the whole pipeline. Looks like interesting stuff. As long as he's not talking about threads and weird warp cores and shit.
Share it with a colleague, friend, or on social
Share it up.
media,
Give
and
these guys a
subscribe
follow,
if you haven't already.
Like and subscribe.
The dream of branch education is to make free and accessible, visually engaging educational
we watched that
videos
video.
that
That
dive
was a good one.
deeply into a variety of topics on science, engineering, and how technology works, and then to combine multiple videos into an entirely free engineering curriculum for high school and college students.
Good shit.
Taking a few seconds
Yeah, they should be showing this in grade school. Wicka-chow. They should be showing this in grade school, honestly. These kids need to know how this operates, because I don't know how it operates.
to like, subscribe,
Yeah, that's why all these kids are what not able to read and write. What did Kayla say? Like, these kids can't even, they're in 3rd grade and they can't even read. They can't count on their fingers, and they're in 3rd grade. She's like, how many is this? And they're just like, fingers. Yeah. Yeah. Cooper can count on all of his fingers. He does the thumbs up. He said, great. He can count to 30. He knows his ABCs. He knows lots of words, lots of colors. He knows how to say more. He knows a lot of animals. He knows how to say more, please. He says thank you. He's very polite, very independent.
and comment below helps us a ton.
Yeah.
Additionally, we have a Patreon page with AMAs and behind-the-scenes footage. Support
them a like.
instruction multiple thread. Thank
Hit
you.
their Patreon.
So now that we've explored how single instruction multiple threads is used in video games, let's briefly discuss why GPUs were initially used for mining Bitcoin.
Yeah.
We're not going to get too far into the algorithm behind the blockchain, and we'll save it for a separate episode. But essentially, to create a block on the blockchain, the SHA-256 hashing algorithm is run on a set of data that includes transactions, a timestamp, additional data, and a random number called a nonce. After feeding these values through the SHA-256 hashing algorithm, a random 256-bit value is output. You can kind of think of this algorithm as a lottery ticket generator, where you can't pick the lottery number, but based on the input data, the SHA-256 algorithm generates a random lottery ticket number. Therefore, if you change the nonce value and keep the rest of the transaction data the same, you'll generate a new random lottery ticket number. The winner of this Bitcoin mining lottery is the first randomly generated lottery number to have the first 80 bits all zeros, while the rest of the 176 values don't matter. And once a winning Bitcoin lottery ticket is found, the reward is 3 Bitcoin and the lottery resets with a new set of transactions and input values. So why were graphics cards used? Well, GPUs ran thousands of iterations of the SHA-256 algorithm, with the same transactions, timestamp, other data, but with different nonce values. As a result, a graphics card like this one could generate around 95 million SHA-256 hashes, or 95 million randomly numbered lottery tickets every second. And hopefully, one of those lottery numbers would have the first 80 digits as all zeros. However, nowadays, computers filled with ASICs, or application-specific integrated circuits, perform 250 trillion hashes a second, or the equivalent of 2,600 graphics cards, thereby making graphics cards look like a spoon when mining Bitcoin, next to an excavator that is an ASIC mining computer. Let's next discuss the design of the tensor cores. It'll take multiple full-length videos to cover generative AI and neural networks, so we'll focus on the exact matrix math that tensor cores solve. Essentially, tensor cores take 3 matrices and multiply the first 2, add in the third, and then output the result. Let's look at one value of the output. This value is equal to the sum of values of the first row of the first matrix, multiplied by the values from the first column of the second matrix, and then the corresponding value of the third matrix is added in. Because all the values of the 3 input matrices are ready at the same time, the tensor cores complete all of the matrix multiplication and addition calculations concurrently. Neural networks and generative AI require trillions to quadrillions of matrix multiplication and addition operations, and typically uses much larger matrices. Finally, there are ray tracing cores, which we explored in a separate video that's already been released. That's pretty much it for graphics cards. We're thankful to all our Patreon and YouTube memberships.
That's pretty much it.
Sponsors for supporting our videos. If you want to financially support our work, you can find the links in the description below.
Yeah, definitely check these guys out. Branch Education. Hit them up, give them a subscription, comment, like. Oh, I forgot to like the video. Like the video. I like the video. Wow, 300,000. 300,000 likes. Oh, wait. I forgot to. There we go. Okay. Where was that one? Go to their videos. That's how GPU. Here, video games.
Video games have
This was the one. So this was the one I was going to watch yesterday when my computer hard crashed on me. Right around now, actually. I'm gonna stop the replay buffer real quick. Okay, we're stopping that. And let me bring up Task Manager again. I just want to see what we're cooking with. Yeah, I still don't love that my GPU is bouncing around like that. I did just update the graphics drivers yesterday. It should not be doing that. I don't think it should be doing that.
Spectacular graphics, capable of transporting you to incredibly detailed cities, heart-racing battlegrounds, magical worlds, and breathtaking environments. While this may look like an old Western train station and locomotive from Red Dead Redemption 2, it's actually composed of 2.1 million vertices, assembled into 3.5 million triangles with 976 colors and textures assigned to the various surfaces, all with a virtual sun illuminating the scene below. But perhaps the most impressive fact is that these vertices, textures, and lights are entirely composed of ones and zeros that's continuously being processed inside your computer's graphics card or a video game console. So then, how does your computer take billions of ones and zeros and turn it into realistic 3D graphics? Well, let's jump right in. The video game graphics rendering pipeline has 3 key steps: vertex shading, rasterization, and fragment shading. While additional steps are used in many modern video games, these 3 core steps have been used for decades in thousands of video games for both computers and consoles, and are still the backbone of the video game graphics algorithm for pretty much every game you play. Let's begin with the first step, called vertex shading. The basic idea in this step is to take all the object's geometries and meshes in a 3D space and use the field of view of the camera to calculate where each object falls in a 2D window called a view screen, which is the 2D image that's sent to the display. In this train station scene, there are 1,100 different models, and the camera's field of view sections off what the player sees, reducing the number of objects that need to be rendered to 600. Let's focus on the locomotive as an example. Although this engine has rounded surfaces and some rather complex shapes, it's actually assembled from 762,000 flat triangles using 382,000 vertices and 9 different materials or colors applied to the surfaces of the triangles. Conceptually, the entire train is moved as one piece onto the view screen, but actually each of the train's hundreds of thousands of vertices are moved one at a time. So let's focus on a single vertex. The process of moving a vertex, and by extension the triangles, from a 3D world onto a 2D view screen is done using 3 transformations. First, moving a vertex from model space to world space, then from world space to camera space, and finally from the perspective field of view onto the view screen. To perform this transformation, we use the X, Y, and Z coordinates of that vertex in modeling space. Then the position, scale, and rotation of the model in world space, and finally, the coordinates and rotation of the camera and its field of view. We plug all these numbers into different transformation matrices and multiply them together, resulting in the X and Y values of the vertex on the view screen, as well as a Z value or depth, which we'll use later to determine object blocking. After 3 vertices of the train are transformed using similar matrix math, we get a single triangle moved onto the view screen. Then the rest of the 382,000 vertices of the train and the 2.1 million vertices of all the 600 objects in the camera's field of view undergo a similar set of transformations, thereby moving all 3.5 million triangles onto a 2D view screen. This is an incredible amount of matrix math, but GPUs and graphics cards and video game consoles are designed to be triangle mesh rendering monsters, and thus have evolved over decades to handle millions of triangles every few milliseconds. For example, this GPU has 10,000-ish cores designed to efficiently execute up to 35 trillion operations of 32-bit multiplication and addition every second. And by distributing the vertex coordinates and transformation data among each of the cores, the GPU can easily render the scene, resulting in 120 or more frames a second. Now that we have all the vertices moved onto a 2D plane, the next step is to use the 3 vertices of a single triangle and figure out which specific pixels on your display are covered by that triangle. This process is called rasterization. A 4K monitor or TV has a resolution of 3840 by 2160, yielding around 8.3 million pixels. Using the X and Y coordinates of the vertices of a given triangle on the view screen, your GPU calculates where it falls within this massive grid and which of the pixels are covered by that particular triangle. Next, those pixels are shaded using the texture or color assigned to that triangle. Thus, with rasterization, we turn triangles into fragments, which are groups of pixels that come from the same triangle and share the same texture or color. Then, we move on to the next triangle and shade in the pixels that are covered by it, and continue to do this for each of the 3.5 million triangles that were previously moved onto the view screen. By applying the red, blue, and green color values of each triangle to the appropriate pixels, the 4K image is formed in the frame buffer and sent to the display. You're probably wondering how we account for triangles that overlap or block other triangles. For example, the train is blocking the view of much of the train station. Additionally, the train has hundreds of thousands of triangles on its backside that are sent through the rendering pipeline, but obviously don't appear in the final image. Determine.
You're gonna be eating lunch? What's for lunch? Gabby Maru. Gabby Maru is here. What's up, buddy? Yeah. It's kind of a, it's kind of a lazy Saturday. Oh, excuse me. Just kind of a lazy Saturday today. So everybody's just kind of vibing, feeling it. I was actually gonna, what's that? Oh, sorry. I was pulled away from the microphone a little bit. No, I was saying it's just like a lazy Saturday. Wait. Go check out Gabby Maru. Gabby Maru. What was I gonna say? I don't know. It seems like a lazy Saturday. A lot of people are out and about, or who knows, but I'm tired. Koopy was at the park, and then all of a sudden he needed a nap, and he's like, bye park, bye trees. So Kat brought him home, and he's napping right now. So, and I was feeling like I need a nap too. I'm kind of tired, as you could tell. Ugh. What is it? Dinner be pepperoni pizza with stuffed tomato sauce crust. Ooh. We don't do stuffed tomato sauce crust. We do stuffed cheese in America. Stuffed crust, stuffed cheesy crust. A bunch of fat asses in America. I don't know. What are we doing lunch, or are we going to a soiree tonight? Yeah. Isn't that a song? I'm not sick, but I'm not well. Excuse me. By the flagpole sitter. Or flagpole sitters. Yeah, it's we got some pretty good cheese crust over here. I'll tell you that much. It's pretty good. But we just watched a video on GPUs, and now we're watching how video game graphics are rendered. Fascinating stuff. It is about trains. This scene is from Red Dead Redemption 2. So, yeah, and Cat, we lost Cat about an hour ago. Oh, 30 minutes ago? Oh, so you understood all that stuff about GPUs?
Determining which triangles are in front is called a visibility problem, and is solved by using a Z buffer.
That is a visibility problem.
Buffer or depth buffer. A Z buffer.
Got it.
Adds an extra value to each of the 8.3 million pixels corresponding to the distance or depth that each pixel is from the camera. In the previous step, when we did the vertex transformation,
it is a very, very calming voice.
We ended up with X and Y coordinates.
We did.
But then also got a Z value that corresponds to the distance from the transformed vertex to the camera.
Okay, I understand.
When a triangle is rasterized, it covers a set of pixels. And the Z value or depth of the triangle is compared with the values stored in the Z buffer. If the triangle's depth values are lower than those in the Z buffer, meaning the triangle is closer to the camera, then we paint in those pixels using the triangle's color and replace the Z buffer's values using that triangle's Z values. However, let's say a second triangle comes along with Z values that are higher than those in the Z buffer. meaning the triangle is further away.
Okay.
We just throw it out and keep the pixels from the triangle that was previously painted with lower Z values.
Got it.
Using this
well, it
method,
could be
only
AI.
the closest triangles to the camera with the lowest Z values will be displayed on the screen. By the way, here's the image of the Z or depth buffer, wherein black is close and white is far. Note that because these triangles are in 3D space, the vertices often have 3 different Z values, and thus each individual pixel of the triangle needs its Z value computed using the vertex coordinates. This allows intersecting triangles to properly render out their intersections pixel by pixel. One issue with rasterization in these pixels is that if the triangle cuts at an angle and passes through the center of the pixel, then the entire pixel is painted with that triangle's color, resulting in jagged and pixelated edges. To reduce the appearance of these jagged edges, graphics processors implement a
anti-aliasing
technique called super sampling anti-aliasing.
Nailed it.
With SSAA, 16 sampling points are distributed across a single pixel. And when a triangle cuts through a pixel, depending on how many of the 16 sampling points the triangle covers, a corresponding fractional shade of that color is applied to the pixel, resulting in faded edges in the image and significantly
what are we even talking about? Yeah, because I'm a designer, so I kind of know what anti-aliasing is. Yeah, I mean, it's common knowledge. Come on.
less noticeable pixelization. One thing to remember.
But, you know, now these graphics cards have all sorts of different anti-aliasing devices. Yeah, he knew it when he was 5. Basically, all it means is making like 8-bit, you know, like Nintendo graphics, how they're all jaggy. This kind of smooths out the edges of, you know, 3D models, or even if it's like in Photoshop where you have 2 layers over top of each other, it's just smoothing out the edge of an object, basically. Just a little smoothery.
Is that when you're playing a video game,
so it doesn't look like jaggy, it looks smooth.
Your character's camera view, as well as the objects in the scene, are continuously moving around.
Right.
As a result, the process and calculations within vertex shading, rasterization, and fragment shading are recalculated every single frame, once every 8.3 milliseconds, for a game running at 120 frames a second.
That is just crazy.
Let's move on to the next step, which is fragment shading. Now that we have a set of pixels corresponding to
I'm still not convinced it's not black magic.
each triangle, it's not enough to simply paint by number to color the pixels. Rather, to make the scene realistic, we have to account for the direction and strength of the light or illumination, the position of the camera, reflections, and shadows cast by other objects. Fragment shading is therefore used to shade in each pixel with accurate illumination to make the scene realistic. As a reminder, fragments are groups of pixels formed from a single rasterized triangle. Let's see the fragment shader in action. This train engine is mostly made of black metal, and if we apply the same color to each of its pixel fragments, we get a horribly inaccurate train. But once we apply proper shading, such as making the bottom darker and the top lighter, and by adding in specular highlights or shininess, where the light bounces off the surface, we get a realistic black metal train. Additionally, as the sun moves in the sky, the shading on the train reflects the passage of time throughout the day. And if it's night, the materials and colors of all the objects are darker and illuminated from the light of the fire. Even video games such as Super Mario 64, which is almost 30 years old, have some simple shading where the colors of surfaces are changed by the lighting and shadows in the scene. So let's see how fragment shading works.
Super Mario. Pronounce
Basic
what?
idea is that if a surface
Rasterization?
is pointing directly at a light source, such as the sun,
That's
it's shaded brighter.
rasterized.
Whereas if a surface is facing
That's it. Rasterization.
perpendicular to or away from the light,
Just means, like, the way I think of it, like flattening an image. Because in like Photoshop, you can have smart objects where you can edit them, but you can rasterize them and just like flatten it into pixels, basically. So that's essentially what they're saying here, rasterizing, because you're taking all the 3D objects and just mashing it down into a flat image. You'd love my brain for a day? No, you probably wouldn't. You probably wouldn't.
it's shaded
Because
darker.
I got brain damage, I'm sure.
In
I'm
order to
pretty sure.
calculate the triangle shading, there are two key details we
Ka-chow!
need to know. First, the direction of the light, and second, the direction the triangle
Most
surface is
handsome
facing.
brain.
Let's continue to
How do
use
you
the
know?
locomotive
I
as
don't
an
even know what my
example
brain
and
looks like.
paint it bright
all full
red
of holes.
instead of black. As you already know, this train is made of 762,000 flat triangles.
Right, of course, as you already know. Yeah, it comes with a bow tie.
Many of which face in different directions.
Whoop, whoop. Love that jam.
The direction that an individual triangle is facing is
Called the normal.
called its surface normal, which is simply the direction
Roasted.
perpendicular to the plane of the triangle, kind of like a flagpole sticking out.
Yeah, she kind of looks like the Joker. And she might be crying. I'm not sure. I think she's crying.
the
in that
ground.
picture. Or
To
that
calculate a triangle's shading, we take the cosine of the angle, or theta, between the two directions. The cosine theta value is 1 when the surface is facing the
master.
light, and when the surface is perpendicular to the light, it's 0. Next, we multiply cosine theta by the intensity of the light, and then by the color of the material to get the properly shaded color of that triangle. This process adjusts the triangle's RGB values, and as a result, we get a range of lightness to darkness of a surface depending on how its individual triangles are facing the light. However, if the surface is perpendicular or facing away, we don't want a cosine theta value of 0 or a negative number because this would result in a pitch black surface. Therefore, we set the minimum to 0 and add in an ambient light intensity times the surface color, and adjust this ambient light so that it's higher in daytime scenes and closer to 0 at night. Finally, when there are multiple light sources in a scene, we perform this calculation multiple times with different light directions.
Multiple times? Who's Colleen sings? Miranda sings. Those are two very different names. What? How did you mess that up? Colleen sings? Miranda sings? No, thank you. What? We're right in the middle of learning about how normals work. Colleen Ballinger? Oh, God. Why? Why does she look like that? No. What if you woke up to that? Oh, my God. She does look like that. Whoop, whoop, whoop. Yeah, she does look like that. What's wrong with this girl? Is she okay? How many drugs is she on? She's a pedo? Well, she looks like a pedo in that picture. Jesus. Is she? What do you mean she's a pedo? She like sleep with a little kid?
No, she got caught.
God. Is that the face she was making when she did it? Jesus. Is she a twin? Look at this. Who's this? Oh, so this is just photoshopped? Yikes. Just yikes. Like, why would you play this? She must have multiple personalities, clearly, because why would you make a character that looks like that and be like, yes, this is it. This is it. No, no, thank you. No, thank you. Oh, look, my diarrhea. Right here. My diarrhea. What? Right here. My diarrhea. Yeah, well, thank you for putting that in my head. Now I know who that is. Gross. All right, back to normals.
Directions and intensities, and then add the individual contributions together.
What was that? Was that Discord? I keep getting like Discord noises. I don't like. Discord? Hello? Hello, Discord? Nope. It's me.
Having more than a few light sources is computationally intense for your GPU, and thus scenes limit the number of individual light sources and sometimes limit the range of influence for the lights, so that triangles will ignore distant lights. The vector and matrix math used in rendering video game graphics is rather complicated, but luckily there's a free and easy way to learn it, and that's with Brilliant.org.
Boom.
Brilliant is a multidisciplinary online interactive education platform and is the best way to learn math, computer science, and many other fields of science and engineering. Thus far, we've been simplifying the math behind video game graphics considerably. For example, vectors are used to find the value of cosine theta between the direction of the light and the surface normal. And the GPU uses the dot product divided by the norm of the two vectors to calculate it. Additionally, we skipped a lot of detail when it came to 3D shapes and transformations, from one coordinate system to another using matrices. Rather fittingly, Brilliant.org has entire courses on vector calculus, trigonometry, matrix math, and graphics algorithms. Alternatively, if you're all set with math, we recommend their course on thinking in code, which is offering incredibly easy. We're sure you Brilliant sign up subscription. Key problem with it. Let's get back to exploring fragment shading. One key problem with it is that the triangles within an object each have only a single normal. And thus, each triangle will share the same color throughout the triangle's surface. This is called flat shading and is rather unrealistic when viewed on curved surfaces such as the body of this steam engine.
I see that.
So, in order to produce smooth shading, instead of using surface normals, we use one normal for each vertex calculated using the average of the normals of the adjacent triangles. Next, we use a method called barycentric coordinates to produce a smooth gradient of normals across the surface of a triangle. Visually, it's like mixing three different colors across a triangle, but instead we're using the three vertex normal directions. For a given fragment, we take the center of each pixel and use the vertex normals and coordinates of the pre-rasterized triangle to calculate the barycentric normal of that particular pixel.
Look at that.
Just like
equation.
mixing the three colors across a triangle, this pixel's normal.
Did you guys learn that in school? This is what I'm saying. Like, these computers are, these are the calculations your graphics card's doing. And it's just like, no problem. Doing trillions of that calculation per second. It's a bundle of silicon and wires. How is it doing that?
Be a proportional mix of the three vertex normals of the triangle. As a result, when a set of triangles is used to form a curved surface, each pixel will be part of a gradient of normals, resulting in a gradient of angles facing the light, with pixel by pixel coloring and smooth shading across the surface. We want to say that this has been one of the most enjoyable videos to make, simply because we love playing video games, and seeing the algorithm that makes these incredible graphics has been a joy. We spent over 540 hours researching, writing, modeling this scene from RDR2.
Oh. Leia wants attention. Leia wants some attention. What time is it? What time is our thing tonight? Yeah, so I should probably sign off pretty soon. But this has been fun, guys.
And animating. If you could take a few seconds,
Yes,
comment below.
Like,
it would help
comment,
us more
subscribe,
than you
share.
think.
I
So
will give
thank
you a
you.
like. Oh, here comes the freaking whatever.
Thus far, we've covered the core steps for the graphics rendering pipeline. However, there are many more steps and advanced topics. For example, you might be wondering where ray tracing and DLSS, or deep learning supersampling, fits into this pipeline. Ray tracing is predominantly used to create highly detailed scenes with accurate lighting and reflections typically found in TV and movies, and a single frame can take dozens of minutes or more to render. For video games, the primary visibility and shading of the objects are calculated using the graphics rendering pipeline we discussed. But in certain video games, ray tracing is used to calculate shadows, reflections, and improved lighting. On the other hand, DLSS is an algorithm for taking a low-resolution frame and upscaling it to a 4K frame using a convolution neural network. Therefore, DLSS is executed after ray tracing in the graphics pipeline generates a low-resolution frame. One interesting note is that the latest generation of GPUs has 3 entirely separate architectures of computational resources or cores. CUDA, or shading cores, execute the graphics rendering pipeline. Ray tracing cores are self-explanatory. And then DLSS is run on the tensor cores. Therefore, when you're playing a high-end video game with ray tracing and DLSS, your GPU utilizes all of its computational resources at the same time, allowing you to play 4K games and render frames in less than 10 milliseconds each. Whereas if you were to solely rely on the CUDA or shading cores, then a single frame would take around 50 milliseconds. With that in mind, ray tracing and DLSS are entirely different topics with their own equally complicated algorithms, and therefore we're planning separate videos that will explore each of these topics in detail. Furthermore, when it comes to video game graphics, there are advanced topics such as shadows, reflections, UVs, normal maps, and more. Therefore, we're considering making an additional video on these advanced topics. If you're interested in such a video, let us know in the comments. We believe the future will require a strong emphasis on engineering education.
Good stuff. There's so much work that goes into video games. It's insane. Absolutely insane. So that's Branch Education, guys. I love all their videos so far. Yeah, we watched the one on printing microchips. That blew my mind. How CPUs are made. This also blew my mind. What was the other one? Oh, inside a hard drive. I wanted to look at that one. What else? How long was that one? That one was 21 minutes. Hard drive's 15 minutes, which she's got to start getting ready pretty soon. Oh, how does the JPEG work? Interesting. Ooh, SSDs. That one's only 10 minutes long. Could watch that one. So what's the difference here? Engineering inside, and then how does NAND flash work? Let's watch this one.
This video is sponsored by Kioxia.
Who?
Solid-state drives are fascinating,
They sure
not
are.
only because they can store terabytes of data, but because they can access any piece of that data almost instantaneously. This solid-state drive can hold 8 terabytes of data.
Damn.
If each bit were represented by a penny faced either heads or tails, that is, a 1 or 0, this drive could store the capacity of 64 trillion pennies. Now, if we laid all of these 64 trillion coins out flat on a surface, the area of the surface would take up the entire state of Massachusetts, which is an incredibly large area to be covered in pennies. But what's truly incredible is that the solid-state drive can find a 5 by 5 meter area of pennies anywhere on this massive surface, and then write to or read out the binary state of those pennies. In fact, the SSD can erase and change the state of every single one of these 64 trillion coins up to 10 times every day, and it can read out the state of all of these pennies around 70 times a day. So, how does it do it? Well, in this solid-state drive, there are 18 NAND flash microchips that are used for storing all 8 terabytes of data. When we look inside a single chip, we find that there's a stack of 8 die. Each die has 2 planes, and if we were to zoom in on a single plane, we would find that each plane is a vast array of vertically stacked charge-trap flash memory cells organized into thousands of blocks. Each block is organized into hundreds of pages, and each page contains tens of thousands of memory cells. And each charge-trap flash memory cell can hold 3 bits of information, or 3 coins worth of data. Here's a nanoscopic picture of what the stacks of memory cells look like, which is just one microscopic section of the overall die. In other episodes, we discussed how information is stored in each cell, or how the pages of cells are organized. But for this episode, let's focus on the big picture and see how this solid-state drive can store 64 trillion bits, and how it can access or write to the contents of just one page of about 10 million pages. Note, however, that these numbers are approximate, and that they're different for different brands and sizes of SSDs. In this solid-state drive, there are a number of components we have to look at. First, over here, is the SSD controller microchip, or brain, whose role it is to interface between all 18 NAND flash chips. This microchip also interfaces and communicates with the laptop, computer, or server that the SSD is plugged into. Aside from the 18 NAND flash chips and the controller, the other main components are the 8 DRAM chips, which serve as a memory buffer for holding the massive lookup tables or translation tables that tell where all the information is stored. We'll get into what this lookup table does shortly. But for now, the other main components are the memory channels that allow the 18 NAND flash chips and the SSD controller to communicate. Each NAND flash chip has a memory channel and is composed of 16 wires or traces that run through the PCB. These memory channels are used for reading the address of where data is located and transferring the actual data to write to or read from the NAND flash. Additional traces are used for sending commands to write to or read out the information to each of the NAND flash chips. To better explain the data flow, let's use a simple example. The computer requests a small piece of information from the solid-state drive, say a picture. The SSD controller then sends the request for the NAND flash chip to read out the contents of chip 9, die.
Huh? Are you going to flatten it? You want to flatten it? right now. What do you mean? Do I have to be available? Oh, he'll be fine. Okay. We're almost done here, right? Yeah, we're like halfway through. We're halfway through. What? Why? We're half. Okay.
4, Plane 1, Block 351, page 45. The 3D NAND flash chip accesses that location and sends the contents along the memory channel's 16 traces back to the controller. This controller then routes the information to the computer that it's plugged into. Or the reverse could happen, wherein the computer asks to store data. The SSD controller would then ask the NAND flash chip to write the information to a particular page, or if the file were larger, the controller would write this file to hundreds of pages instead of just a single page. You might wonder, how does the controller keep track of where all the information is stored? Well, that's the role of the lookup table or the translation table. From the perspective of your computer, the SSD is just a massive set of sectors of data, each the size of 512 bytes. And thus this 8 terabyte drive has 15 billion sectors. For example, when you store a picture, your computer tells the SSD to store the picture's data in a set of unused sectors. The SSD controller then takes the picture's data and sends it, noting the address for the chip, die, plane, block, and pages of the precise location. The SSD controller essentially has a massive spreadsheet where all the sectors are translated into different locations inside the 18 different NAND flash chips. Note that this type of translation is also called a logical to physical translation, where your computer only sees what sectors the picture is stored in, but the SSD knows the physical locations. Furthermore, the translation table, or lookup table, is continuously being updated. When it's in continuous use, it can be found in the working memory, or DRAM chips, of the solid-state drive. And when it's not in use, it's saved to the 3D NAND flash chips. Another important detail is that while individual pages can be written to or read from, it's more common for superpages to be utilized. A superpage consists of all the pages on each of the 18 chips that share the same die, plane, block, and page designation, and thus the superpage has the same address in each of the respective 18 NAND flash chips. For example, when a large video gets saved, it gets spread across all 18 NAND flash chips and stored in a superpage, or possibly multiple superpages. Thus, when writing to or reading out the video, all 18 chips are running in parallel, resulting in read or write times faster than if the video were stored in just one of the NAND flash chips. Furthermore, superblocks can also be utilized, and they're the common block address among all 18 NAND flash chips. Also note that the SSD controller performs other functions like wear leveling, garbage collection, and executing the error correction code, but these topics will be saved for a future video. This is the fourth video that explains how solid-state drives and 3D NAND flash work. This video focuses more on the SSD architecture, while the other videos explain the structure of the 3D NAND flash, how information is written to a cell, and how...
in a future video. But I think I'm going to sign off, guys. I appreciate y'all being here. What are we at? Hey, we're at 1,600. It's been bouncing up and down, but this is a huge milestone. 1,600 subscribers on the tech channel. So thank you guys very much. Is that how you're wearing your hair? No. No, I don't think you should wear your hair like
No, I'm gonna wear it down.
No.
Like, wait.
No.
I'm not gonna wear heels.
She's wearing flats. You should wear your big pink flat rubber.
Should I show my shoe?
Yeah. Go wear your pinkish flappish. Pinkish flappish. But hey guys,
These are my house shoes.
these are her big rubber house and baiting shoes.
I got them at Ollie's bargain store.
They were like $1.
They were $4.
Something.
They're comfortable though, right?
Maybe for you. They don't fit my feet.
Okay. Why
Yep,
are you
so
wearing my shoes?
they're not really fitting. So anyway, guys, Gabby Morrow, Cat Spade, thank you for being here. I think you were the only two that were here today, and Botrix.
And my other personalities.
And your other Botrix. So, but hey, thank you for being here, and we'll see you on the flip side. Peace.
Please.
Peace.
Please.
Ended.